We present Vitruvio, a conditional variation autoencoder to generate building meshes via single perspective sketches. Architect Mario was savoring his favorite espresso at the bar when he unexpectedly ran into Anna, a businesswoman urgently searching for an architect to design her new company office building. Sensing an opportunity, Mario quickly grabbed a napkin and his trusty pen. He had just 20 seconds, espresso drinking time in Italy, to make an unforgettable impression. The project's location was key, and Mario's mind raced with ideas. He began sketching different building shapes and masses, aiming to demonstrate how they would fit seamlessly into the building site and context. Within those 20 seconds, he wanted to explore 3 distinct shapes, analyze their volumes and proportions, and illustrate how they would harmonize with the surroundings. Mario's hand moved swiftly, sketching elegant structures, but he needed to convey their 3D implications effectively. The clock was ticking. Mario's heart pounded as he showed Anna the sketches, explaining the ideas behind each shape. However, without the ability to present their 3-dimensional consequences, the sketches fell flat. Anna appreciated his effort, but couldn't fully grasp the potential of the designs from the 2D napkin sketches alone. In that fleeting moment, Mario missed the chance to secure Anna as a client and set the project on the right path. The encounter taught him the importance of preparation and having the right tools to bring his visionary ideas to life. Mario vowed to be better prepared next time, ensuring he could capture the imagination of potential clients and turn his creative visions into reality. Mario returned to his office and quickly realized that current workflows are too expensive and impractically time-consuming. The existing software relies on Gen AI to translate sketches to images and then to 3D models, which is inefficient. Mario decided to train his own AI model specifically for building designs. However, he encountered a major obstacle. There is no comprehensive dataset of both sketches and buildings. Existing datasets, like those from Fedorova, Tono et al., BuildingNet, and BuildingGAN, provide segmentation, depth masks, and 3D parts, but lack sketches and real building examples. The only dataset with geolocated buildings, Real City 3D, unfortunately, also lacks sketches of those buildings. So Mario hired us, a team of AI researchers, to overcome these limitations. We took the Real City 3D dataset of geolocated buildings from the municipality of New York and generated synthetic sketches in a perspective view using suggestive contour style. We also meticulously tracked their location and orientation within the dataset. For the 3D representation, we employed an occupancy field, which uses a simple binary classification to indicate whether a 3D point is inside or outside the mesh volume. This approach allowed us to create accurate and efficient 3D models from the generated sketches. Specifically, we tracked the orientation of each building and trained 2 main AI models to understand its impact on reconstruction quality. We used the oriented bounding box to align all the buildings to a canonical pose, meticulously recording the rotation angle for each building. This approach ensured that our models accurately accounted for orientation, improving the overall quality of the 3D reconstructions. We trained a conditional variational autoencoder based on the Occupancy Network using 2 main datasets, training 1, preserving the building orientation with their relative position to true north. Training 2, aligning the buildings to a canonical pose. Once Mario identifies the building site, he can create a sketch. We then analyze the differences between the 2 models based on this sketch to determine how orientation impacts the reconstruction quality. We demonstrated that preserving the building's orientation helps capture more fine-grained details in complex building shapes, as it effectively identifies and retains outlier and less common structures. This approach ensures a higher accuracy and richness in the reconstructed models. This work has the following limitations. The network's performance is dependent on the viewpoint, the human style of the sketch, and the final representation. Consequently, it may not perform well in typical sketching scenarios, as evidenced in the supplementary materials. We encourage readers to explore the approaches discussed in the referenced papers for further insights. We invite future researchers to contribute to the development of this dataset by completing the form on our project website. Your participation will help realize a vision where multiple stakeholders can collaboratively enhance the 3D shapes and information of buildings. Starting from quick perspective sketches, this collaboration will validate mass and proportion within the context and, most importantly, allow Mario to explore the implications of different mass shapes, such as L, C, and circular forms. This approach not only assesses proportion and volume, but also incorporates other building-related information, ensuring that the project is on the right sustainable track from the very first sketch. As a summary, in this paper, we introduced a learning-based method for single-perspective sketch-to-3D applications in the architecture, engineering, and construction industry. We adapted a previous state-of-the-art conditional variational autoencoder, Occupancy Network, to scalable datasets. We showed qualitatively and quantitatively how the building orientation affects the reconstruction. Thank you for your attention.